All right, so I'm going to be talking about how we're leveraging Sumo at Fetch for a specific use case of trying to understand how we can improve our product. All right, so let's see if I can move down. All right, so there's three topics that I'm going to try to cover. One is what we call the cloud robotics platform, what that actually means. And then the type of challenges that are unique to robotics, which is primarily what I'm going to be focused on in this conversation, in this talk. So I've got about 10 minutes to try to explain to you all of robotics. And that's after the food coma. So, all right, and then how we're actually starting to leverage Sumo Logic to solve those sort of nuanced problems. So by the way, after the conversation, I'm actually going to be around and hopefully I can try to answer more of those questions. This is going to be high level in terms of the robotics specialty side of things. All right, so let me just talk to you a little bit about Fetch. So robotics, we do robotics, it's in the name, but it's not your typical type of robotics, at least what a lot of people would think. It's not humanoids, it's not Roomba, it's not very consumer facing. We're focused on warehouses. And there's sort of two solutions that we provide to warehouses. One of them we call virtual conveyor. This means moving goods within the facility. And then the second one is collecting information about your facility, and we call that data survey. Not very complicated. In terms of the actual robotics platform, we have three robots. One of them is called Freight 100. It's one of the first ones that we built out. And then the second two offerings that we're actually working on right now, end of the year, we're going to hopefully release them. 500 and 1500, and they're named that because that's the weight in terms of the kilogram capacity that they can carry. So the robotics hardware platform, there's three of them, but they're designed to allow us to kind of produce and manufacture accessories on top of them. And the accessories are either geared towards helping you move product or collect information about your inventory. So moving product, that's definitely the biggest thing that we're involved in trying to solve. Again, virtual conveyor. So the first thing we worked on was actually the HMI shelf. We bolted on a shelf, we put on a display, and that allows people to basically have these robots positioned near where people are picking stuff off of shelves, put that onto the robot, hit a button on the robot, that sends it off, and it's going to go and then you continue picking off the rest of the items. The second one, and I'm going to come back to this actually later in the presentation, is the cart robot. So the biggest thing is it's a lot cheaper, and then it's also got a lot more space. So less good for us because we sell less robots, but good for the customers because they can have more carts and they can move more product. So it's definitely the best-selling kind of product that we have right now. And then there's a couple of other ones. Roller top, you can attach to a static conveyor, unload things autonomously, drive to the next point, and then reload things. All right, and then the final one is sort of the tag surveyor. That falls into our data survey thing. It's the primary thing that it's trying to collect information about is all the inventory that's marked with RFID. Okay, so the other quick thing I'm going to mention is what we call the cloud robotics platform, a fancy name for three primary things that we try to solve in terms of the cloud. So one of them is configuration. The thing that we're focused on is definitely making robots as easy to use. Robotics is still pretty hard. Robots are not very easy to use in terms of configuration, managing, errors happen, weird behavior. So configuration is something that you unpack the robots, you drive it around, and then you go to our cloud platform, and then you can configure what we call workflows by simply, actually there's a language called Scratch. It was invented by MIT, and we kind of enabled that. It was meant for teaching kids how to program. So you can do simple things like, hey, I want my robots to go to this area, and I'm going to talk about the HMI as an example here. I want these robots to go to an area, display these buttons. If they click a button, I want it to go to the next location where either I'm going to put more stuff onto the robot or take stuff off of the robot. So that's one thing that you can do. Configuration is part of it. The second part is monitoring in terms of where your robots are, what they're actually doing. Are there any errors, whether it's Wi-Fi related errors, whether it got lost. And you can see in real time what your robots are actually doing, where they are. And then the final piece is the data analytics side of things, and that's of course focused more on the data survey product side. So collecting information about your inventory, things that might have been missing in the inventory. It's actually surprising, but warehouses actually lose hundreds of thousands of dollars worth of inventory, whether they didn't get shipped or someone forgot where it was actually placed, and over time you might refind it. So you send a robot, it continuously surveys, collects information, and then now you've got autonomous ability to, in real time, understand where your inventory is, how it's moving, and then you can hopefully make efficiencies and optimizations in terms of how product is moved and placed. All right, so one of the other things that we do focus on, and this is sort of the intelligence part, so this is less kind of customer facing, but the division between the robotics platform in the cloud and the on-robot kind of software, there is a significant amount of the portion of the intelligence actually lives on the robot itself. There's too much data to communicate between the cloud, and you need to process it in real time. So to some degree, you can kind of abstract the kind of division of intelligence as one example being sort of Google Maps and you. Google Maps gives you this high-level plan, and so does the cloud robotics platform to the robot. Hey, I want to get to this location. It'll give you this high-level plan, but it doesn't really know, not necessarily with real accurate information around what is the car right in front of you, what lane you want to actually try to take. That kind of division is that processing of real-time information about what are the cars in front of you, when do you actually need to brake, maybe there's a collision that that was just obstructed path. That's all things that the robot is actually doing. It might go back to the cloud and say, hey, this top-level plan really didn't work out, give me a new one. The cloud will say, okay, based off of the traffic patterns that I've understood about the entire environment from all the other robots, here's another path plan that you can try to take. All right. So really high level, but hopefully paints somewhat of the picture in terms of what the cloud robotics platform is providing, and then what the on-robot kind of division in terms of the intelligence is. A lot of the intelligence is actually on the robot. And that's actually where I'm going to be talking about the Sumo Logic part of things as well. How am I doing on time? Okay, so let's move through this really quickly. All right, so I hate this slide the most, primarily because I'm stealing credit from at least two people. One of them is right there. He's the lead engineer, did most of the Sumo Logic stuff. So if you actually have real questions you want real answers into, that's the guy. That's the guy right there. And then at least the second person, I'm going to actually give a shout out to Alex. He's been great. He actually works at Sumo. He helped us kind of get set up and provide training. One of the other bigger reasons for why we ended up going with Sumo. Great support. So in terms of my background really quickly, I actually got into software through robotics. I joined the robotics club back in high school, became president, and then college as well. I went to UC Berkeley, obviously did CS. And most of my background has been on the kind of web-based technologies, everything from kind of working on Chromium and the embedded framework. This is before Electron came along, working with V8, and then all the way to the cloud services side where I worked on a little bit into distributed services. I also had to work with COM, if you guys know what that is. And then at Fetch, I'm now the software engineering director. I actually originally started about 4 years ago, where I was actually making a lot of this stuff. These days, I just email and steal credit from people like Samit right there. So, all right, that's enough of me. All right, so the Sumo Journey. All right, I got my notes here. Okay, so one of the things that we're trying to do in terms of the product itself, after 4 years, a lot of what we've kind of shifted into is not really just adding new functionality, but improving and sort of supporting our existing functionality. Our robots actually are able to, navigation being a huge part of it, they're actually able to go from one location to another location. We're trying to solve that problem as well as possible. That's a lot of where we're now starting to focus on. Are we getting from one destination to the other destination as quickly as possible, as efficiently as possible, and even from the human perception, as intelligently as possible? You don't want robots in a really crowded environment sort of jerking, trying to go to the next location. All of that makes an impact in terms of the product being successful too, and in terms of just the impression. All right. Okay, so let's see, hopefully I covered. So because of the fact that we were now focused in terms of just trying to understand how well we're doing a good job of that, we've run into the challenges that are sort of more unique to robotics in terms of trying to understand when things actually go wrong. And I'll talk about a little bit more in terms of what wrong actually means. All right, so let's actually kind of jump into the robotic side of things a little bit more. Okay, so this is going to be the most challenging part about it. So unlike many, I'm not going to say like all, but unlike many other kind of engineering-based problems, the part of the problem starts at the input side of things. a lot of the input that's coming into the robotic side of things are very, very unconstrained. They're almost infinite, and they actually make an impact in terms of the robot behavior. So it starts with the sensors. We've got a lot of sensors, especially the big robots. The little robots get away with just only having like a sensor in the front in terms of depth and LiDAR. But you also have IMU, which for most people, they know what accelerometers are and gyroscope, and that's what an IMU is. And we've also got odometry and encoders. But because of the fact that they're trying to deal with very analog kind of data, and it's highly variable, not just within one customer at a given time, but across different customers, you don't really necessarily have a perfect understanding of when things go wrong, how things went wrong, and then more importantly, how you go about trying to reproduce it and analyze and then classify what actually led to the behavior that was undesired. For example, a robot jerking, trying to go to a different path, and then a different path, and then it finally went to the location that it was intending to go to. Okay, so there's a lot of different input. They're highly varied. You've got light sources that are different. They impact the LiDAR data. Sometimes things reflect back really, really strongly. We ran into a situation, we didn't even know about this, where at certain aisles, for safety reasons, warehouses have these mirrors up top so they know when forklifts are coming. That caused the LiDAR data, because LiDAR bounces data like light off of the objects, and it made the robot think that there was something right in front of it. Things like that. Sometimes the floors, sometimes there's carpets, or highly like polished grounds. And so one way we try to figure out how much we've moved is using the encoders, which tell you how much the wheels have moved. But if you've got a certain load on the robot, highly variable, you don't know how much they've decided to put in 24.5 grams, maybe they went over the 100 kilogram capacity, you don't know. There might have been a slip. You might not have actually moved. So you've got to try to correlate as much of this data from all across the IMU, the LiDAR, and do your best approximation in terms of where you actually are. And where you actually are is a very, very closely tied problem to navigation. Things are highly symmetrical, environment changes, robots often get lost, in fact. Okay, so those are the kind of high-level, unique kind of problems, and that's what when I say probabilistic, that's what it means to say probabilistic kind of problems. You've got highly dynamic environments and so many inputs with so many variations that it's hard to just kind of simulate all of that into one environment and then consistently reproduce it. It's just untenable. So, sort of two challenges come up from all of this, this inherent problem of robotics. One of them is, when do you know when things went wrong? And wrong here means maybe it didn't go to the location as quickly as you wanted it to, or as smoothly as you wanted it to. Some cases are a little bit better known, things like mislocalizations, you can know that. And then, how do you reproduce it? Because if I'm an engineer, I'm going to try to fix it. One, if I'm going to try to debug it, I've got to have some understanding of how it went wrong. I'm going to reproduce it and then go through all the various stacks of the code to see where things might have gone or what are the assumptions that I made. And then after I reproduce it, how do I actually verify that things, reproduce it? And then hopefully I came up with a theory of how to fix it. I put in the fix. How do I verify that it actually fixed it? And who did it fix it for? Because again, these environments are highly variable. When you tweak a lot of this code, you're impacting the behavior more generally. It's not specifically for that nuance of, I was in this position, these are all the things that were in front of me, these are the specific light sources, whether it was the sun, and this was the specific floor. I'm going to try to solve this problem as generally as possible without impacting, without regressing the other environments where I was doing well. Okay, so all right, so at a high level, there are all these different engineering challenges, but at a high level, what do I really care about? I care that the robot got from one location to the other location as consistently, robustly, quickly, and intelligently as possible. The other thing I care about is my ability to actually communicate with the cloud robotics platform and ask, hey, I need to get to this other location. I should have the ability to communicate this data, and we try to compress and minimize as much data as we can, but there's a lot of data to communicate, so I need Wi-Fi. The other very important thing, like I mentioned, was I want to make sure that these robots are where I intend them to be. All right, 5 minutes left. So, so the way to solve this problem, obviously, and especially when 4 years ago we had 3 or 4 customers, how we actually went about solving this problem was we'd get a complaint. or some issue, some field application engineer or support is proxying this concern. Engineers, whether it's late at night, in the morning, whenever, we'd go SSH into that robot. We try to communicate with the customer as much as what was going on as best as you can. We grab what are called ROS bags, these huge files with all the LiDAR data, all the 3D data. We pull that up into this thing called, well, it's like this, think of Maya, if you know. Basically, you can try to, as best as possible, reproduce using all the data, replay what the robot was at least seeing. And then you'd hopefully put in a fix, and then you get the patch out to the customer, and then you'd work with the customer to say, hey, let us know if things are actually, if things happen again. Over time, we solved the problem, but now we've got hundreds of customers. Completely untenable for us to go into the robot, figure out what was going on, pull out all the data, which takes a very long time. Some of these customers, sometimes on 3G, believe it or not, honestly. So became very untenable very quickly. So the way to solve this problem, one of the ways that we solved it, or trying to solve it, and in some cases very successfully, and I'm going to talk about those three things, is through data. And so when we started looking into solutions, we started with the data ingestion side of things. Okay, so we've got a lot of problems to solve, and we don't necessarily want to go about trying to solve this data ingestion problem, especially for this specific need. There are specific cases for us in terms of analyzing traffic patterns, and we have to correlate the data, analyze the data, actually programmatically understand the data, and that's for like customer needs. But in this case, we don't want to build in the infrastructure of collecting these files and actually streaming it up to the cloud. So that ended up being one of the biggest reasons why. One of the biggest concerns when we started evaluating other tools to try to solve this problem. And the other thing is, as an engineer, it wasn't too long ago that I was actually writing code, so I empathize with this still well enough, is that I don't actually want to worry about also how to produce this data. If it's structured data, it's going to take me a little bit longer to produce this, ingest it, and then get it working. I just want to be able to ideally spit it out into some log file, and then something takes care of it, and on the other end I want to be able to analyze it. And if that data ends up being valuable, maybe I'll put in some effort to actually more formalize, structure it, and put it into the actual system itself. And it might be useful for customers as well. So we did consider alternatives. And again, I'm going to point you to the real person who actually did the work there, Sumi. But the main things that we consider, and we actually do use ELK to some effect, was ELK, and we quickly realized that there were part of the biggest inconvenience was actually collecting the data from the robot itself. Sumo provides like a really good utility. I can go into the actual application itself and say, hey, there's a new log file that I want to add. A huge problem in terms of actual data consumption and CPU usage. I really don't want to be competing for the navigation stack in terms of CPU resource. Again, all of that compute is actually on the robot. I don't want to spend that CPU resource or memory resource or network resource. So I can limit all of that, control all of that through Sumo Logic, and specifically the collector side of things. So we also considered FluentD, but the biggest thing there honestly was the fact that we really did not want to spend the time in terms of configuring FluentD. It does do a really good job, and I think they've made a lot of progress, but the other part of this was actually the fact that Sumo Logic provides other tools that we use them for. So one of them is just simple kind of debugging, stack traces, log reduce, time compare, and that's actually what we're going to be using, or I'm going to quickly try to show you. But obviously the biggest thing that what we more recently this year started to work on was how we can kind of statistically quantify changes that we make, starting with the QA environment actually. So currently the way the QA works, as engineers I'm sure we all know, QA is your first customer. They're going to try to use your product, and they're going to give you some feedback. With robotics, if I put in a change where it's more like at this time, at this location, or certain locations, I want the robot to move around obstacles, dynamic obstacles, in a particular way. We literally have to have people looking at the robots as constantly as possible, and to actually determine that. And it's not a very scalable way of trying to understand whether these code changes actually had the impact, the desired impact. And also just the overhead of sometimes communicating that with QA. And the other thing we actually tried to do was put cameras on top of all the warehouses that we have in the QA environment to try to automatically determine if the robot has the desired, or just give us anomalies. Did the robot get lost? Did it stop too many times? So Instead, we started to use actually Sumo Logic for this. So there are three things that I'm going to just quickly try to talk to you about. One of them is mislocalizations. If I make a change, I want to know whether if I make a change that's intended to deal with certain environmental changes that improve the robot's ability to understand where it's at, then I want to be able to tell even in the QA environment and moreover even in production. So very quickly, here's an example where and this actually happened in our QA environment. It's not really this bad typically, but very quickly we were able to say, okay, so 1 week ago, we spit out some new data that said, hey, I'm mislocalized. Mislocalized is also the challenging kind of, but in certain cases we can accurately identify, hey, I'm mislocalized, which means the robot is lost. Very quickly we were able to run a query that says, hey, in this given week, like the past week before we introduced the change, what were the number of mislocalizations that happened? And then the next week after the change, what were the mislocalizations that happened? And in this case, there are these 3 robots that we had in the QA environment that we were trying to monitor, and very quickly we were able this was actually a real thing that we were trying to solve, and it previously required humans to come in, relocalize, like first find a robot that's lost, and then kind of relocalize a robot, and then start that entire process again. This quickly allowed us to both gain the statistics and know when things are mislocalized, quickly correct it, and a human doesn't have to be aware of it. All right. So sometimes environmental changes impact it. One issue, I know kind of boring, but Wi-Fi hugely impacts it. A lot of our customers, because they're warehouses, they don't necessarily have the best Wi-Fi connectivity. So sometimes we actually say, hey, look, a lot of the behavioral impact is due to these Wi-Fi. If you just put in another access point, we're very confident this is going to improve the situation. And so very quickly we're able to monitor the number of connection drops. Things that we're going to try to improve is in which areas and across different customers. And sometimes there's things like metal shelves that also impact the Wi-Fi connectivity. All right, so I'm actually out of time, so I'm going to really quick. One other thing that we are now starting to use Sumo for is also trying to understand how customers and how frequently the customers are actually using the product itself. At the end, all those metrics should end up with customers wanting to use our product more. So very quickly, we can actually just run simple queries that lets us understand that, hey, and this is a customer that we quickly deployed to, they had to change workflows, how quickly they actually adapt to using our robots. That helped us understand that over a month, this cart connect, which is like attaching to a particular cart, moving it, how frequently they're actually using it. All right, so I went through this really, really quickly. I apologize, but Sumit and I will be here. I'm going to yield the stage to someone else, and let's be honest, we're pretty sleepy. All right, so just in case, yeah.